last module for today. Did you have fun with PyTorch? All right, so this is going. You need to continue this, and you need to practice more to discover everything that you can do with PyTorch, and then combine it with what we will see here to be able to do things. Now, you created tensors, you loaded images into PyTorch, and you did things to your images. All right. So we are halfway there. We can read the data. We can create the weights and tensors. Now we want to do the next steps. Before we move on, let me make sure that we understand the eigenvalue, eigenvectors properly. So remember the problem we looked at here, where we had a matrix of 6, minus 1, 2, and 3. We want to compute the eigenvalues for this. Okay, so eigenvalues are values, are numbers, are scalars. All right, and because this is two-dimensional, this will give us two eigenvectors, two eigenvalues, and two eigenvectors. So we did this, as you saw, and you can go back to the slides and click on the link and follow the steps to see how exactly we computed that if you forgot. But we basically solved the equation of determinant of matrix minus lambda times identity equals 0, and we solved it. We found the solutions. The solutions are two eigenvalues, which are lambda equals 5 and 4, which means I have a vector that if I multiply my matrix by this vector, it gives me the same vector multiplied by the first eigenvalue, which is 5. All right? And now, what is this vector? I have to solve this equation to find out. So yes, so I'm looking at the first one. Okay, so I'm for every eigenvalue we have an eigenvector. We have a corresponding eigenvector. Okay, so I want to find the eigenvector that corresponds to eigenvalue of 5. To compute it, I multiply these two together, and I get 6 times v1 minus v2 equals 5 times v1, and then 2v1 plus 3v2 equals 5v2, right? Now, if I multiply this one by 3 and then sum them over, I get 18 here minus 3 plus 3, so that gives me 20 v1 equals 15 plus 5 is 20 v2, right? No? v1 plus v2, yes. 15 v1 plus 5 v. I'm so dirty. 15 v1 plus 5 v2, and that tells me v1 and v2. v1 equals v2, and I put it back in here. So 2v1 plus 3v1 is 5v1. Useless. Yeah, so this is 6v1 minus v1. We made a mistake somewhere. But if we know how to do multiplication and solve the equation, we can solve this, and that gives us V1 and V2. Okay?
But this is like you get both of these are equal, so they're both 1/√2.
Of course, yes. So V1 and V2 are the same, then so this is 1 and 1. Okay? So we have the first. Thank you. Are this on tape? Can we delete this? So we have this matrix has an eigenvalue of 5, and the eigenvector corresponding to that is 1 and 1. Okay? As an assignment at home, you do you repeat the same thing with the second eigenvalue, and find the second eigenvector. All right? And see, so then you will see that this is how eigenvalues and eigenvectors are computed, and then we can put them together and build the matrices.
I'm just trying to remember, is the number of eigenvectors the same as the rank of the matrix?
Yes. The number is the same. In some cases, so let's say you have a 5 by 5 matrix, you expect to have 5 eigen values, right? And 5 eigenvectors. In some cases, some of your eigenvalues are duplicate. So some of them are the same. In those cases, we call them degenerate cases. And you don't need to worry about it. Just forget about it. It can happen. But you have 5. You have n of them. In general, some of them could be equal. All right?
Are there eigenvalues for matrices which are not identical?
Eigenvalues for matrices are in general not identical. They could be identical or not.
Okay.
But in general, they are not. You have n eigenvalues for an n-dimensional matrix.
Okay.
All right? Good? And you had an exercise. You saw how you compute eigenvalues and eigenvectors with PyTorch, right? Yes.
So is every eigenvector orthogonal to each other?
Eigenvectors are not necessarily orthogonal to each other. Eigenvectors are not necessarily orthogonal. They are? I'll answer that next time.
That's an exercise.
I want
Yes.
to correct myself. I asked the wrong question. Actually, I was interested in whether there are eigenvalues for not squared matrices.
Eigenvalues for not.
For n times m or n times r matrix, not squared.
So.
Okay, so I have the answer to the previous question.
Yes.
Well, Google has the answer to the previous question. In general, for any matrix, the eigenvectors are not always orthogonal, but for a special type of matrix, symmetric matrix, the eigenvalues are always real, and the corresponding eigenvectors are always orthogonal.
Right. Thank you. And that's why we can factorize them in the form that I showed you, in this form. Now, if we have a matrix that is 1, 2, 3, 4, 5, 6, and we have a vector that is v1, v2, right? When we multiply this, what do we get? We get a vector that is 3 by 1, right? So it's not. It doesn't satisfy the requirements for the eigenvector. All right. So let's move on. we have a lot more to discuss. We have a lot of math to cover tonight. My screen is shared. Everyone can see. Google is behaving. Great. All right. So non-linearities. Where are we in our network? We talked about the linear algebra part here, and now you can see this part is the dot product, is the matrix multiplication that we talked about. This part is the addition, and this picture is familiar with everyone. Knows what we're talking about? Yes? Okay, great. Then so we multiply the weights by the inputs. We add the bias, and then we apply a function on top of that. And we saw in the overview part 2 weeks ago, we saw that this is actually crucial if we want to be able to approximate any complicated function with this. And then we get an output, right? Now, here we want to talk about this function here that we apply after doing the linear algebra. So this is called, these are called affine maps. Fancy name for saying that I have a vector of inputs or a matrix of inputs. I multiply them by weights and then add bias to that. That's it. All linear. These are all linear multiplication and summation. And in PyTorch, it's done very nicely. You define you say that I want to do a linear function, and you define the dimensions of your function. Then you define your data. In this case, I'm simulating it, but usually you get the data from the input. This is the input that you read, like it's an image that you load, or a text that you load, or a voice, or whatever. And then you say lin of data. That's it. You apply your linear function to your data. In the exercises, you will experiment with this in about 20 minutes to make sure that you know everything about applying affine maps to your input data. All right. Now, what happens after that? Remember the thing that we saw here? We want to know what sigma is. And this is from PyTorch tutorial. This is this is a nice way of putting this. Let's say that I decide my second function to be a linear function again, another linear function with different multipliers and summations and a different bias. So if I apply f over g of x, so g of x is given by this, cx plus d, and then I apply f to it. So that means I take g, multiply by my a, and add b to it. And then I simplify that. This gives me matrix A multiplied by matrix C times the input plus a number, which I can rename it as a matrix plus a bias. All right? So that means if I pick my activation function, this is called the activation function, because we think we are simulating a neuron with this. All right, it's a super simplified version. So the activation function, if it is linear, it is not doing anything for us. It's just more multiplication, and then at the end we are not better off than having just one simple function. All right. By the way, what are these values in an affine map? The values in A, in the weights and in bias, they are picked randomly, and you will see this in the exercise. They are randomized in the beginning, and then during the training, we learn the values of our weight matrix and the bias vector, and they are learned through this process. All right. The activation function cannot be linear. What is not linear? Non-linear functions. So we have to work with non-linear activation function if we want to add information at the end of it, which we show it as this. This is again the same equation that you saw. Now the question is, what kind of function can we pick as an activation function? We need the function to have nice properties when we take the derivatives. And why do we take derivatives? Who has done machine learning here? You know how we find a solution to any problem. We start from a point, and then we have to find the minimum of our cost function, and we have to take derivatives of our functions because we have to know which way to go, right? So the functions that we use throughout, we need to take derivatives for. So let's say, okay, I want to use a flat function. What is wrong with this as my activation function? It is linear, and when I take the derivative, it gives me 0. And when I have 0 derivative, I cannot, no matter what learning rate I pick, I cannot move anywhere. I cannot learn anything. All right. Next one. If I take a step function, right, it is 0 almost everywhere, and where it is not 0, it is useless. It is something that does not exist, right? So this again, this is useless, not useful. But if I make it a little bit smooth, it does magic. If I take the sigmoid function, which looks like this. It is nice because I can take the derivative. The derivative is given by the sigmoid function itself, and it has a bell shape. Historically, a lot of you who started learning deep learning when deep learning was very young must have used sigmoid functions. But the problem with the sigmoid function is that if you look at it, again, the derivative is 0 in most of these places, right? And that's not a good property. Plus, you have to compute an exponential at every point. Computing exponential is not fun. It's expensive. So, but what else do we have? We have tan H, hyperbolic tangent, which has a derivative that again looks like it has a bell shape, but it goes to 0 much more slowly than the sigmoid. This is something that we usually use. And by the way, in PyTorch, these are used as torch.tanh, and you give it your whatever function tensor that you have. The most popular one is called ReLU, and it is very sophisticated. It is 0 if your input is less than 0, and it grows linearly if your input is greater than 0.
We have to take a square root function.
Yeah, you can do a lot of other things. the thing is what you need is something simple that has a good derivative that doesn't go to 0 very quickly and is easy to compute. So this is what we use. It's simple enough and it works.
What do you do with the derivative at the point?
What do you do with the derivative at 0? I don't know what we do with the derivative at 0. I think I think we set it to we set it to 0 if it is on this side, or to a fixed number if it is on the other side.
So you don't learn whatever happens on this side. If I may interject, you don't use it, right? Because it's useless.
But
right?
we had the same argument for the step function.
No,
and we didn't like that
no.
one.
Over there,
It's
everything
everywhere.
is.
That one is everywhere. It's 0 everywhere.
So that function is totally useless. This function is useful on the right side.
See, this doesn't learn here because your derivative is 0, and you don't learn for when you're.
What about some parabolic function? It wouldn't be much more useful.
Yeah, you can use different functions. It comes down to what really works and whatever you can get to work and is fast and not expensive. All right. Then one more thing that you need to know is you're doing a yes.
Can we go back to the previous slide? So you're saying that you don't use the part of the function where the derivative is 0 because you don't learn.
No, you use it, but it doesn't really help you learn much on this side. Yes.
But that's part of the non-linearity. That's what makes it non-linear. So you get
That's
zero
the only
somewhere.
thing that makes it non-linear, right?
Correct. And that's you want that property. Otherwise, you would have a linear. And
Yeah, because this is linear.
Yeah, that's what I'm confused.
So doesn't this function goes to infinity very fast when x is like large value? That's why the sigmoid like capped it between like when x is more extreme like a wider value, but you still kept the slope like slower, but this one goes to infinity very fast.
It doesn't go very fast. It's linear, so you have to really go to infinity for it to go to infinity. A linear function is a good function. Yeah. If you had something like this, that would be a disaster.